So this is the concept map of this unit, which is modern physics. We circle around quantum mechanics throughout the unit, so I'll divide into two parts. The first part is about photons, which is the introduction of the quantum mechanics, and the second part is the matter waves, which really dig into what quantum mechanics is. So for photons, we have a case which is called the photoelectric effect, and I included a problem for this case. But basically, photons, we would say it is not a matter, but it is quantized with certain energy. And when we're looking at matter waves, we're looking at matters, and matters, they have mass. So it's kind of weird for saying a mass have a wave. So that's why the wavelength is not the usual wavelength we deal with the usual waves, but instead it is called the de Broglie's wavelength, which convert one's mass or the momentum, which is the velocity, mass times velocity, to the wavelength. So we're saying that everything that has a mass has its wavelength. Then we could look, we will look at this wave function later, but we should look at here first about the Bohr's model of hydrogen and the hydrogen-like ions. We have two equations here linking to this Bohr's model of hydrogen, but I included one problem here, which explains most of the inside of Bohr model of hydrogen. But as an introductory, I would like to illustrate this diagram first. This is corresponding to n is equals to 3 of an electron in a Bohr model of hydrogen. And we could see that it is actually wave-like, which is what the de Broglie's wavelength is talking about. Electron, it is wave-like. Well, anything has mass is wave-like, but when it is electron, then the wave property is more significant. And what wave does is like, there's nodes here, 6 nodes here, and these 6 nodes is actually indicating that it has to, the electron has to it's not the electron, the atom has to contain a quantized number of orbitals. In this case, the orbital is 3. And when we have a quantized number of orbitals, then we would have a certain number of velocity of the electron moving around the orbital. And so that's why this thing is constant. And this is the number of orbital. This is the atomic number. And we could see that the radius of the electron is quantized. The same with orbital. So the velocity is also quantized. Then when we move on, we not look at the Bohr's model of hydrogen, but instead we look at real atoms. And for real atoms, we first look at the Pauli's exclusion principle, which says that no two electrons in an atom can have the same values for all 4 quantum numbers, which is here the quantum numbers. There's 4. The first one is called the principal quantum number, n, denoted by n. The second one is called the angular momentum orbital quantum number, denoted by L. And they have a relationship is that n has to be greater than L. So when n is equals to 2, then L has to be 1 or 0. But if n is equals to 1, then L has to be 0. And then the third one is called the angular momentum projection quantum number, denoted by ML. And oh, sorry, I forgot to mention, for angular momentum orbital quantum number, L, it has symbols here, S, P, D, and F, which is easier for I don't know if it's scientists to use. But for angular momentum projection quantum number, it is describing the z component of the angular momentum, and the ML is related to L by this. This is not really equation, but if n is 3, then L could be 0, 1, 2. This would be n, this would be L, and ML has to be from 0. When L is 0, then ML has to be 0, but if L is 1, then it could be -1, 0, and 1. But if it is 2, then ML could be -2, -1, 0, 1, and 2. And then the fourth component is the electron spin, which is just ms denoted by ms with a positive 1/2 or a negative 1/2 value. So as we go further, we're looking at the atomic transitions in multi-electron atoms, and it follows one particular rule, which is called the selection rule. The selection rule is followed when there is an absorption of photons or emission of photons. And I would use an example as the sodium. The sodium atom has this electronic configuration, but what we're focusing is this outermost electrons. So this electron here, there's an electron here. It could be spin up, it could be spin down. But what we're focusing on is how does this electron excite when it is absorbing a photon or it is colliding with another particle. So here I just draw up to 6s, but it could go up more, 7s, 8s. But for here I use 6s to illustrate how the selection rule is going with sodium. So everything has to start with the ground state. And there's two absorption. One absorption is via collision and one absorption is via photons. So when it is via photons, then it has to follow the selection rule. So it could only go here to 3p, 4p, or 5p. And if it is collisional, because collisional, the particle has a mass, so the energy could be converted into the kinetic energy of the particle after it collides. So it could actually jump up to any energy level when it possesses enough kinetic energy. And then so this 3s could actually jump all the way to 4f. It's okay because it's collisional. But when we're dealing with emission of photons, it has to follow the selection rule again. So if the electron, let's say it via collision of a neutron and it jumps up to 6s, then it has to follow the selection rule, which is the only outcome is 5p. Then 5p, this is not the only route. It could go to 5p, 4p, or 3p. And then from 5p, we could go to 5s, 4s, 4d, or 3d. So there are so many possible outcomes, right? So here I listed it all. And as we move forward, we're looking at the wave functions. So the wave functions is normally surrounded by the electron. We're looking at what electron does. But it could be anything. It could be proton, it could be neutron, it could be some particle with some small masses. Because it's only the small masses that makes the de Broglie's wavelength significant. So we're saying that for any particle that's small enough, well, it's significant to study, that they have a wave function. And this wave function, if we square it, then it would be the probability of that particle inside the space. Inside a certain space. So it is actually given by the Schrodinger's equation, which its definition is connecting energy and momentum of a wave function, and it is just a result of quantized energy. So any wave function that comes out from the Schrodinger's equation means that it has a certain number of states, and it is not continuous. So if we square the wave function, we take the absolute value of it, we have the probability of the matter inside a certain space. And we're looking at 3 different cases. The first case we would look at is the particle in a box case. The particle in a box case is given by this simple definition, which is saying that the particle is inside a potential well, that its boundary, its potential energy is towards infinity, and the particle cannot escape from that boundary. So this is given by this equation. And we see here when the n is equal to 3 at the number 3 state, then it should have 3 antinodes. At 2, it should have 2 antinodes. And when it's 1, it should have 1 antinodes. And if we have to square the wave function, then it would be something like this. And for number 2, it would be something like this. We have to square the wave function. And for number 1, it's like this. So the second case we look at is the finite potential well. And when we look at finite potential well, there's a very interesting aspect we should deep down is the quantum tunneling. And the quantum tunneling, we have 3 different equations, which looks very complicated at first, but as I go through, it's actually more simpler than I thought. So the n, which is not really n, I have no idea how it's called, I forgot, but it is called the penetration depth. The penetration depth is given by this equation, which I'll explain a little bit more later. And this is basically a diagram illustrating what a finite potential wall might be. So here, this is the infinite potential wall, but so it has to be a node here. And here is the finite potential wall, which you see this doesn't have to be the node. So this line represents the potential energy, bounded inside the well. So this would be the potential energy, and then this would be the kinetic energy of the particle. So as we can see, as the particle is moving towards the center, the kinetic energy is larger. As the kinetic energy is larger, then the wavelength, the de Broglie wavelength would be smaller. It would have a smaller probability, and the amplitude would actually be smaller. So if we have to draw the wave function square, it would be something like this. And then here, and then smaller here, maybe a little bit smaller. Maybe a little bit smaller here, and then it would go here, go a little bit higher, and then eventually it would reach it would reach somewhere, maybe here, I don't know, maybe something like this. I didn't draw it on scale, but this is what the wave function, when we square it, the probability would look like. So here I set n is equal to 7, and we could count there's actually 7 antinodes. But the main focus is the penetration distance and the penetration depth. So in classical physics, when the particle, hits the wall, it would just go back. But in quantum physics, we're saying that when the particle hits the wall, when the potential energy is not towards infinity, then there is some chances that this particle would actually dig into this wall to here. And how does this occur? Would it still be wave-like? Well, when the wave hits at here, it would just decay exponentially towards the nodes. So this line here is something like this. So if we go over the equation, the first thing we're saying that, so if the wave function here in the first path is some wave function, would it be the same here? It is not. And the wave function denoted here is given by this equation. Phi h would be the wave function value at here. So it would be, so if this is x equals to L, then this would be phi of L. And and the penetration depth is how deep that this penetration could go. So in this case, this would be the penetration depth. And the penetration depth is given by here, which we could see that the penetration depth could go more if this energy difference, which is the U naught minus E, is actually smaller, or the mass is smaller as well. This mass of the particle is smaller as well. Because if it's smaller, then it possesses a greater de Broglie's wavelength properties. And the final equation here is saying that what is the probability of finding the particle when it is inside the tunnel? And it is given by this equation here. And it's nothing special, to be honest, here. And the third cases we're looking is the harmonic oscillator. The harmonic oscillator is given by these two equations. And if we compare it to the particle in the box, it's actually similar things. The particle in the box is saying that as n goes upwards, then the energy difference would be exponential. But in harmonic oscillator, we could see that n is actually linear. So if this is n equals to 3, maybe this is n is 2. By the same distance, this would be n is 1. By the same distance, this would be n is 4. This is called the harmonic oscillator, some special property of it. And it's just given by an energy barrier with a parabola shape. So we have to sketch it. Then here we have the we actually have the highest kinetic energy. So the wavelength, the amplitude would be smaller here, and here would be larger. And that's basically all about wave functions and about quantum mechanics. Thank you so much.